Thanks, you guys, for coming. My name is Tony, and this talk is going to be about making big data smaller. And to be honest, I'm nervous, so I'm not sure about your curse, but I'm nervous, and if you see me drinking water, it's just my nervous tick. And every time I do that, hopefully I get a little more calmer. If you guys have any questions, feel free to ask. So a little bit about me. I'm from San Francisco, and in San Francisco, I organize the San Francisco Bay Area Machine Learning Meetup Group. So if you guys are ever in San Francisco and like this sort of topic, feel free to hit me up. Feel free to join the meetup group, and we do events once or twice every month. I'm also working on a site called SF Data Jobs, and the main premise behind that is if you're looking for a job in San Francisco, I want this to be like the premier source for it. There's countless people who come to me and ask me, "Hey, Tony, what startups are what startups in the Bay Area are doing machine learning, and which one would you recommend?" So I got tired of people asking me that, so I just created this list of machine learning jobs in San Francisco, or machine learning companies in San Francisco, and that's that right now. And it's going to be, I'm hoping to turn into a job board. I'm hoping to turn into more than that soon. As for my background, I come from a computer science background. I have a master's in computer science with focus on machine learning and computer vision. And for the past 4 years, I've been a data engineer at ad tech company, and more recently, I've started doing consulting work. So this talks about big data, but what does data mean? Well, a lot of people can think of data as the raw data, but for this talk, we're going to think of the data as the data that's been cleaned, that's been transformed, that has its features extracted. So essentially, we're going to look at data that has this sort of matrix form that you see down here, where there's M observations and there's capital D features. So basically, our data is a huge ass matrix. So, what is big data? Actually, I'm not too sure myself. So I went on Wikipedia and looked it up. And Wikipedia says, big data is an all-encompassing term for any collection of data sets so large and so complex that it becomes difficult to process them using traditional processing applications. So for me, what does that mean to us? What does that mean to me? To me, that means you have so much data that it gives you out-of-memory errors in Python. You have so much data that you run out of disk space. You have so much data that you get your S3 bill and you're just crying. So much data that you're willing to set up Spark, you're willing to set up Hadoop, you're willing to set up your own cluster, and I'm not sure how many of you guys have done it. That's a big pain in the ass. So if you have big data and you're willing to do that, it means you're willing to do a lot. So one question that comes to mind is, can we make big data smaller? And if so, what are the benefits of having smaller data? So just off the bat, the benefits of having smaller data is reducing our storage costs. Our S3 bill is going to be a little lower. Another benefit is we're going to use less computational time to process our data because the data is smaller. And hopefully we won't run into any more out-of-memory errors. And what are some ideas for making data smaller? One idea is maybe we just reduce the number of observations. One way is maybe just keep the observations that are important to us. Whatever that means, whatever important means. Another idea is maybe we don't want redundant observations. Whatever redundant means. Maybe we just remove redundant duplicate data. Another idea is, it's kind of crazy, but just randomly sample the observations. Maybe we'll have some really dense data to begin with, and maybe just randomly sample from it, and we'll get something that, in my opinion, represents the data pretty well. But you know what? The focus of this talk isn't about reducing the number of observations. For this talk, I want to focus more on reducing the number of features, which I think is a little more interesting, or at least in my opinion. So what are some ways to reduce the number of features? One way is just to figure out which features are not useful, throw that shit out. Another way is maybe taking features and combining them to make them more useful. And maybe we should do something clever. I'm not sure what that means. Maybe this talk will answer that. And before we start, I want to give you guys a real-life example of how I use feature reduction in my life. So about a year ago, I started picking up boxing. And in the boxing class, after the first month, I learned enough to get into the ring spar. Got my ass whooped, but that's fine. And what I've noticed was that when someone's punching me, it's a good idea in boxing that when someone punches you, you know when to block or when to back up, right? So the key key thing that I want to predict is when is this guy going to punch me? So what I did first when I was a newbie was I would look at his head, I was look at his arms, look at his shoulders, look at his foot, and when he comes in, especially with his head, I'll notice everything. I'll just react to that, and I'm observing a lot of data points there. And as I progress, what I've noticed is it's a bad idea to look at the guy's head because he can be looking at you in your eyes and he just punch you down low, right? So the head is not a useful information. It's not a useful feature. Another idea is the arms. This guy can be faking you. You never know when it's going to come in. So in my opinion, when you see him like lunge in, especially with newer folks, when you see them lunge in especially with their hips, it's like that's a good sign that this guy's committing to a punch. So it's time to raise your guard. So that's an example of feature reduction in real life, I think. All right, so what about this talk? Again, we're going to be focused on reducing the number of features. So we start off with this data, this M observations by big D features, this big matrix, and we're going to reduce the number of features by doing some magic, and we're going to get this smaller matrix where it's same number of observations, but the features are a lot smaller. And when we do this, we want to preserve the distances between the observations. So let's say we have just 2 random points in the original matrix. The 2 points in the reduced matrix should have sort of a similar distance. And why is this important? Well, what are some algorithms you guys use? Anyone like K-nearest neighbors? I love it. It does well, right? Let's say we take some observation let's say we do K-nearest neighbors for the initial matrix for some observation. If you do the same K-nearest neighbors in the reduced matrix, it better come out to be the same, right? Whatever the nearest neighbors are. So that's why preserving the distance matters. Okay, so here's a question for you guys. Let's say we have this plot of these 4 observations in 2D. How can we make these observations go from 2D to 1D? So each point, instead of representing it as an x, y number, we want to represent it just one number. Any ideas? No? Right. I have one idea. Well, before I get to that, these little dotted lines are just the distances between the points. I didn't draw the one. I left out the one from the far end to just make it a little more clear. But this, again, is just a plot of the observations, and the dotted lines are just the distances between them. And so the question is, how do we represent these points in 2D, the observations in 2D as just one number? Or, sorry, how do we represent these 2D observations as 1D? So one way we could go about it is, why don't we just get rid of the y information? Why don't we get rid of the y-axis? Why don't we just project down into the x-axis? Why don't we collapse all the points down to the x-axis, right? And so that's called projecting the observations to the x-axis. And I color-coded the distances here, and you see what the distances are when you project it down. So these points, this point comes to here, this point goes down here, and so on and so forth. So these 2 points come down to this line, and their distance is this, which is sort of similar to this red line up here, right? I think that does pretty well. So, it does okay on the x-axis. What about the y-axis? What does that look like? So we'll project onto the y-axis, and you'll see that it doesn't do that well. The distances aren't really preserved. You see this orange line here? It becomes really tiny right here. So, so far I feel that we're getting good results by projecting it down to the x-axis. But what if that's just an artifact of the data being like spread horizontally? And would this technique of just projecting it down to the x-axis and y-axis still work if the data was rotated a little bit? So let's rotate the data, maybe by 45 degrees or so. So it's going to look like that. And why don't we just do the same thing we did before? Why don't we take these points and project it down to the x-axis? So now these 2 points get this sort of distance. This blue point, these 2 points here have this sort of distance, and so on and so forth. And the x-axis doesn't look too bad. It doesn't look as good as before, but the y-axis now starts to look a little better. Right? Feel free to stop me if you guys have any questions. So the question then becomes, projecting down to the x-axis and y-axis, that's fine and all, but is there a better coordinate system that we can project down to? We rotate the data, maybe there's a way we can rotate the axis as well so that we can project it down onto it. So why don't we do that? Why don't we just find something? I'm looking at the data, and we know a priori that we kind of projected it 45 degrees. So why don't we have a coordinate system that's also rotated by 45 degrees? So here's the new coordinate system. And let's do this. This is one dimension, one direction of the coordinate system. This is another one. This is like the new coordinate system's x. This is like their y. So if we take these points and project it down to these new coordinates, or this new coordinate system, we'll get this right here, this right here, this here. So this is projecting down to the x, and this is projecting down to the new y. Does that make sense to you guys? Yeah. And so we can see that this is a lot better than what we had here. Agree? And so the real question is, how do we go about doing this, and how does it relate to dimensionality reduction? Well, here's the thing. You have this new coordinate system here, and we just want to represent any of these points as one number. You just drop whatever axis you don't care about. Does that make sense? No? Yeah? No? Yeah. Okay. So we talked a lot about spread, and what's the formal definition of spread here? For this talk, spread is, I'll consider it as the variance. So once we have the points projected onto whatever direction, we'll take the variance of that, and that'll be our spread. And we want to find the projections that has the largest variance or the largest spread. And so the question becomes, how do you determine the observations in the new coordinate system? This might answer, if some of you guys are confused, this might help answer it for you guys. So let's take this point P. So in the original XY axis, P is some amount this way and some amount this way, right? Everyone agree? So what is it now with respect to this new axis? It's some point here, it's up some direction here, up some direction here, right? We want to know, the reason why we want to know what it is in this new axis is so that we can just know what it is, what the value is here, what the value is here when we project it down to these axes. So to figure that out, I just read out some linear algebra here. I can go over it real quick if you guys want. So with this direction, this coordinate, it's represented as some vector, and you just multiply it by P's original coordinates in the XY axis, original XY axis, and you'll get this component. And you do the same for this vector, and you get the same part. So you'll get this coordinate of this new P in the new coordinate system. So the main idea is, you have the new coordinate system. How do you represent the point in the new coordinate system? And that's important because once you throw away different coordinates, like how we did before, where we just drop the x or we drop the y, it becomes a lower dimensional representation. That's all it is. So just reading the observation that finding the coordinate system that's aligned with the spread gives us good coordinate system for dimensionality reduction. And directions parallel to the spread of the data maximizes the inner point distance. So just a rehashing of what we said earlier. So the question is, how do we actually find this aligned coordinate system? Is there a tool developed for this? Well, there is. It's called PCA. Anyone heard of that? Familiar with that? Yep. PCA. So PCA stands for Principal Component Analysis. And basically all it is given a set of observations, find an aligned coordinate system like what we did before, where the first direction, or the first direction of the new coordinate system contains the most spread, and then followed by the second, followed by the third, so on and so forth, where each coordinate or each direction has to be orthogonal to each other, or orthogonal to each other. And to actually compute this, it's going to require O of m cubed. What that means is, we have m observations, it's going to take at least m cubed times to solve that. And the reason why it's doing that is because it's doing like singular value decomposition or solving for eigenvalues and whatnot. So that's all fine and dandy, and probably some of you guys don't really care about what the math is or how it really works, and you just want to have the tool set to use it, right? So here's how you would actually use it. And it's real simple. It's a couple lines. So let's say you have an X, which is a matrix of M observations by D features. You import this sklearn decomposition, or you import PCA from this module over here, and you instantiate this PCA class with the number of components that you want to reduce your original dimension to. So you have a big D over there, and now you want to make it into small d. So now you have this PCA variable. Now you fit your data to, now you fit the data to, now you use PCA to fit the new coordinate system to the data. And now you take the data and you transform it into the lower dimension. And at the end, it'll give you a M by small d matrix. That's all it is. So you guys go home right now and just play with that. You'll see the data being transformed into a lower dimension. And it still has inner point distances preserved. Again, just to make the point real clear, what we just did was we have this matrix small m by big D, and we transformed it to m by small d, which is a lot smaller than before. And we preserved the distance between the observations. And here's what it looks like. Here's an example data in 3D. Here's some data. We fit a 3D coordinate system to it that this long axis here maximizes the spread, the second one maximizes the second spread, and so on and so forth. And we want to do dimensionality reduction, all right? So we know that this third direction here doesn't give us much spread, so we just remove that. And so now we just have this V1, or now we just have this two-dimensional sort of plane. And we graph that out, it looks like that. So let's mess with, I'm a vision guy. Let's mess with some real data. So what if our data is images? How do we represent an image as an observation, right? How do we represent an image as a point in graph, right? So here's this image of a guy's face. It's basically a 100 by 100 matrix where each element is sort of a pixel intensity. So how do you represent a matrix as a point, right? Well, one thing that we can do is we take each row of the image and just string it along together. So we just basically vectorize it out. We just flatten it out, and we get this 100 by 100 dimensional vector, which is 10K, right? And so one question is, given this, can we go back the other way around? Given this 10 dimensional vector, can we go back to this image matrix? And we can't. We just chop it up by hundreds and just restack it, right? And so here's another guy that we vectorized, or here's another guy that we represent as an observation or as a 10K vector, and we just plot it into this graph. So here you notice that there's 10,000 features, and so there's 10,000 components here. And so we plot some more faces, and now if we run PCA, we're going to find the new coordinate system where it has 10,000 directions, 10,000 coordinates, right? So that's fine and all. Now, what does that mean for us, right? Well, remember how I said that a vector can be represented as a matrix, image matrix? Here's the idea. Why don't we take these coordinates and why don't we represent them? So each coordinate can be represented as just a vector, right? And why don't we take the vector of the coordinates and represent it as an image? Why don't we just restack it into an image and visualize it? Well, if we do that, we'll see that the very first coordinate has this sort of face right here, and the second one has this face, and so on and so forth, and this is the very last one. And we'll see that, well, this is more of the coordinates being visualized. So we'll see that a face can be represented in the new coordinate system as basically weights for different coordinates. So here's an original image, and there's 10,000 coordinates for the coordinate system, and we have a weight for each one of them. So what if we threw away a lot of them? Well, what would happen if we just kept 20 and represent the image that way? Well, we'll get something like this. This looks sort of similar, but it's a little fuzzy. Why don't we increase it to, say, 90? Increases it to 90, we actually get something that's fairly similar to the original image. I can't tell the difference. And so what we have here is we're able to do compression using PCA. And just as a quick note on what we're doing here, the original, for one image, we originally had to represent it with 10,000 values. For compressing the image, we only need to have the 90 weights to actually get it to something that we can recognize. And in addition to those 90 weights, we need to have those 90 components of that coordinate system that we were talking about. So for one image, it doesn't make sense to do this compression. But say for a 200 image, so in the original, if we want to represent original 200 images, we would need 200 of these 10,000 vectors, right? If for a compression, we just have this, the 90 axis or the 90 coordinates and the 90 weights for each one of those. Does that make sense? Yeah. All right. So it makes sense to use this technique when we have 90 or more images to compress. So keep in mind that the runtime's n cubed for PCA, and we need to keep around that the matrix, or we need to keep around the new coordinate system to project down to, which is d by d, and requires. And the caveat here is, to run PCA, you need to actually read in all the data points to actually compute the new coordinates, and compute the spread. And it works really well for data that's sort of linear, but what if the data was curved like this down here? Would PCA work for it? Probably not too well. So here's a crazy idea. Why don't we just create a small d by big D matrix, P, where the elements are just randomly drawn. And so now we have this matrix. It's just a random ass matrix. And let's say you have some point in big D space. You multiply by it, and now you just get a representation in a smaller d, right? How many people think that works? No? Maybe? Well, when I first heard about it, I was like, no way it works. So let's see, let's try to get the intuition for it. So in PCA, we were talking about like finding this new coordinate system that aligned with the data, right? So what random projection says is, I don't care what the coordinate system is, just give me some random ass coordinate system. So I'll find them some random direction here, then I'll rotate here, and whatever. And you can see that it kind of works if whatever your coordinate isn't like too off, and there's not a lot of positions where it could be really off, right? So if I projected it down here, it won't look too bad. And maybe if I randomly draw another one, it'll look like that. It's not too bad. So that's sort of the intuition behind it. And intuition's fine, but you want mathematical guarantees, right? Oh, and just keep directions here. So the question is, what is the safe value for D? Well, there's a really easy answer for that. It uses this function here inside the scikit-learn random projection library. So you just need to specify how many observations you have and how much error you're willing to tolerate, and we'll get to that in a second. And it'll give you the number of dimensions that you need in order to safely project down the data to a random subspace. So here's a guarantee. So given 2 points, this original distance will be 1 minus epsilon off from its projected distance, or is bounded by, the projected distance is bounded by the original distance with the plus minus factor of 1 minus epsilon. And you're guaranteed that if you have a dimension of greater or equal to 4 log m, blah, 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 blah. And you don't need to worry about that. All you need to do is plug in your variables here, and it'll tell you how much you need to put in, how many dimensions you safely project down to. And the practical usage of this is, there's a high probability that projection will be good, but there's still a chance that it won't be good. And in that case, one way to safeguard against that is create a bunch of random projections, and as you're going through your data, just keep note of which ones are doing well, which ones aren't, and just throw away the ones that aren't doing well. And so just a recap of what we talked about. So PCA tries to find a line coordinate system where the coordinates sort of maximizes the spread. It runs in f cube time and requires all points to be read in, which kind of sucks. And then it requires m by d space. It requires a projection matrix as well. For random projection, it finds the random coordinate system, and it requires a d by d matrix to do the projection, and is guaranteed to work with high probability. And all right, that's it. Any questions? It was a lot smoother when I did in practice, but. Well, thank you guys for listening to me. Hopefully that was entertaining. Hopefully that was useful. Feel free to ping me if you guys have any questions, or if you are on San Francisco and need someone. Sure. Yes, sir.
Are you going to put this presentation somewhere?
Sure. Yeah, absolutely. Yep. Yep. And some more references if you guys want to play around with it. Yeah. Well, thank you guys.